Hello, everyone. Thank you so much for giving me the opportunity to give this talk today. In the following, I'd like to very briefly basically talk about our ongoing work on constraining cosmology and baryon physics from two-point functions. And I would like to stress that this is very much work in progress, and I'm currently trying to figure out what to make of all of these results myself. So if you have any comments or feedback, please send them to me. I'd love to have them. The work I'm going to talk about, we've been mainly doing together with Joe, David, and Paco, as well as several other members of the CAMOS collaboration. So I think as we've been talking throughout this meeting now, is like these are super exciting times for cosmology, as current and future data are really giving us a lot of basically experiments are going to give us a lot of data at a precision that we haven't seen. And these data are really going to allow us to probe cosmic fields down to very small scales and actually see all the rich structures that we have in these fields. And a very powerful way to actually access these small-scale information is the cosmic shear power spectrum. Now, the problem is that the matter power spectrum, so the quantity actually underlying the cosmic shear power spectrum, is severely affected by baryonic effects. And usually how we basically get theoretical predictions for these effects is that we run hydrodynamical simulations and then measure basically the impact of baryons on the matter power spectrum. Now, the problem currently is that we have a suite of a lot of different hydrodynamic simulations which actually make significantly different predictions for these effects. And just to give you an idea of that, this plot here shows a compilation of basically the predicted effects of baryons on the matter power spectrum coming from a set of different hydrodynamic simulations. And these actually mostly differ in sort of like how they model physics that they cannot actually resolve. So basically how they model, like in subgrid physics modeling. And these uncertainties are really a big problem, and they're currently limiting weak lensing surveys significantly. And these problems are only going to get worse with more precise data in the future. And so it really means that in order to be able to optimally benefit from the exciting data that we're going to see very soon, we really need to learn more about baryons. And we can observe baryons using several different cosmological observables, such as, for example, their X-ray emission. We can also observe them using the CMB as a backlight through the Thermo-Zuniaev-Zeldovich effect. And finally, fast radio bursts are basically starting to also emerge as a potential probe of the baryon distribution in the universe. And in our work, we've sort of decided to take a step back and basically perform a highly simplified and idealized analysis and try to understand how well we can actually constrain both cosmology and astrophysics from the underlying two-point functions that basically underlie all of these observables. And to this end, we've mainly focused on the autocorrelation of the electron density and the cross-correlation, PEE, and the cross-correlation between the electron density and the matter density, PME. And in order to investigate these quantities and basically forecast their constraining power, like look at their constraining power on cosmology and astrophysics, we've used simulations, and specifically we are using the CAMOS suite of simulations, about which we've already heard from Paco yesterday. And as we've heard from Paco, CAMOS is a suite of more than 2,000 small volume hydrodynamical simulations that have been run on a vast grid of cosmological and astrophysical models. And they've also been run for two different subgrid physics modeling, Illustris TNG and SIMBA. And the plots here on this slide basically show the electron distribution that for exactly the same initial conditions that is obtained in Illustris TNG and SIMBA. And as you can see, these two are actually quite different. Especially in SIMBA, we see a much more diffuse electron distribution that we do in Illustris TNG. And these differences actually give rise to basically give differences to give rise to significant differences in basically the response of the statistics that we're looking at in our analysis to baryonic feedback. And this slide here basically shows PEE as a function of the wave vector K for both Illustris TNG and SIMBA as a function of the baryonic feedback parameter to which they respond mostly. And as you can see for Illustris TNG, we basically find this power spectrum to mostly respond to this parameter called ASN1 in CAMOS, which basically quantifies energy-driven supernova feedback. Whereas for SIMBA, on the other hand, we find PEE to be most responsive to ASN2, which quantifies wind-driven supernova feedback. So this really means that these differences in subgrid physics actually give rise to significantly different responses of these two-point functions on to baryonic physics effects. And so before we went on to actually see how well we can constrain baryonic physics from these statistics, we wanted to try to come up with a measure that is observable and mostly independent of simulations that actually allows us to quantify the effects of baryonic feedback on these power spectra. And in previous analysis, it has been found that the baryon fraction in halos seems to be very promising for that. And so what we've basically did in our analysis is to basically perform a very simple exercise where we've taken basically a neural net and tried to predict the power spectra in our simulations from the cosmological parameters as well as F-bar. And the results are shown here on this slide, where you can see the simulations in solid and the predictions from the neural net in dashed. And while you see we completely fail to predict the very extreme baryonic feedback cases, we actually find that the network does a decent job at predicting basically most of the cases for our power spectrum with an averaged relative accuracy of approximately 20%. So given these results, we can now go ahead and basically forecast constraints on both cosmological and astrophysical parameters. And as the astrophysical parameter, we basically take F-bar. And for this analysis, basically, we again do a very highly simplified and idealized analysis, and we basically do exactly the opposite as we did before. So we train a neural network to basically predict the cosmological and astrophysical parameters from the power spectrum, as well as their statistical uncertainties. And this is shown here on this plot, where you can basically see the comparison between the true value of omega m and F-bar and its prediction from a neural net that has been trained on Illustris TNG. And evaluating these error bars, we actually find that this sort of exercise allows us to constrain omega m to basically a relative accuracy of approximately 6% and F-bar to approximately 16%. So these error bars are really small, especially given the small volume covered by the CAML simulations. And so basically the main question here becomes, now what are actually the systematic uncertainties associated to these types of analysis, right? Can we actually believe these statistical uncertainties or not? And in order to investigate this question, we follow an empirical approach. And as we've basically seen already from Paco's talk and a couple of slides before, the CAML simulation suite has basically been run for two different subgrid physics models, Illustris TNG and SIMBA. And the constraints that we've seen so far have been basically derived from Illustris TNG. And so if we now make the assumption that basically our systematic uncertainties on subgrid physics can be captured in the difference between SIMBA and Illustris TNG, we can actually test the robustness of the constraints that we've obtained from PEE by evaluating our illustrious TNG trained neural network on SIMBA. And the basic idea is that if the constraints from PEE are actually robust to subgrid physics, then we should be able to infer basically the cosmological and astrophysical parameters when evaluating our neural net on SIMBA. If this is not the case, on the other hand, the biases that we detect can serve as a measure for our systematic uncertainty. And the results from this exercise are shown here on this slide. And you can basically see this is exactly the same as the plot before, basically predictions versus truth. And you can see that actually the network seems to be doing a reasonable job at basically recovering both F bar and omega m when tested on SIMBA. And this means that at least in fact, when we basically compare the bias on the parameter that we obtained to the error bars, we actually do not find that bias to be significant. And this means that at least from the in the CAMELS volume, it seems that the electron density auto-power spectrum actually seems to be a possible way to robustly constrain both cosmology and astrophysics. And this already brings me to the end of my talk. So during this talk, we've really seen that baryonic feedback uncertainties are limiting current and future weak lensing surveys. And so it is really crucial for us to obtain constraints on the baryon distribution from observations. And there are many different, many possibilities with FRBs, I think, being a very exciting probe. And in our work, we've basically done a very simplified and highly idealized analysis and basically tried to see how well we can forecast cosmology and astrophysics from basically the power spectra underlying all of these statistics. And from the tests that we've performed so far, it seems that these constraints seem to be largely robust to subgrid physics uncertainties as implemented at least in Illustris and SIMBA, which means that it might really be worth to further pursue the electron density power spectrum as a possible probe to constrain baryonic feedback. Having said that, the analysis that we've performed has been highly simplified and idealized. And a couple of the main caveats I see are, first of all, that the electron density power spectrum is not directly observable. So it remains to be seen how well these results translate when we actually look at the actual observables. And we've also completely neglected any observational systematics on small scales, such as, for example, for weak lensing blending. And finally, I would also like to point out the main challenges that we faced in this analysis. And I think the main one has really been the stochasticity in the CAMELS simulations due to the small volume that they're covering. And I would also like to point out that this kind of translation of our results from Illustris to SIMBA actually only works for a subset of the power spectra that we've considered. And with that, I would like to thank you all very much for listening. And again, please send me any comments you might have.
Thank you very much, Andrina. So are there any questions? Yes, Rachel.
Very nice talk, Andrina, and beautiful work. As you mentioned, of course, the CAMELS boxes are very small. Have you experimented with using your trained network to apply it to a dark matter only simulation in a larger volume and see if, for example, you can reproduce what you would get for TNG 300 or something like that? So to use your method to expand the volumes that you can make predictions for.
That is actually a great idea. So I haven't done that yet, but I think that's definitely something that that I would love to do, and maybe chat also more with you about it. Yes, definitely. Thank you so much.
Yeah, that would be great. Thank you.
Yes.
Yeah, very nice talk. So I'm not sure I understood how it's possible. I think it was for TNG that you get F bar wrong, but omega m still right.
Oh, so yeah, you mean the bias that we see at high F-bar values?
Yes, yes, exactly.
So I think the problem with this one is the following. So like in basically, how can I say this? So in so most of the models in the Latin hypercube have a pretty low F-bar, like baryon fraction F-bar. And there's only a couple with very high ones in Illustris. And so I think that this turnover and the bias is actually due to the fact that our training set, which is this like Latin hypercube in camels, does not have a lot of very high F-bar simulations. And so I think this is just the bias that we're seeing. And the weird, like the why I think this is the case is that if you look at then like Simba, which has intrinsically lower baryon fractions, actually you don't see this bias. And I think it's basically just like a lack of training data. Yeah.
But it's interesting that you still get omega m, right? That's what is like, yeah, there was the same, like omega m and F bar, like the plots were from the same input, right?
I agree. I think to fully answer your question, I think I should probably look at like the ones that fail on F bar, if they also fail on omega m or not, right? Like I'm not, because like I should be color coding them.
Yeah, it's not the same. I understand. I thought it was the same. Okay, yeah, that makes sense. Okay.
Okay. If there are, oh yes, there's one more question there from Bruno.
Hi, Andrina. Thank you so much. I just wanted to ask you, so what is the closest observable to the electron density power spectrum that we can find in data?
So I think sharing my like big excitement, I think it would be the FRB, basically like the cross correlation of the FRB distance measures, basically. The autocorrelation of FRB distance measures, because like basically can I say this dispersion measures? Because basically like the FRB dispersion measure is kind of like basically a probe of the integrated electron density from the FRB to us. And this is actually how all of this project started, like trying to see if we can use FRBs to constrain baryons or not.
That's really cool. Thank you.
Okay, perfect. Well, thank you very much, Andrina. And we will now move to Christina Kreisch, and she will talk about precision cosmology with voids in the machine learning era.
Excellent, thank you. So yeah, today I'll be discussing a paper that we put on arXiv this July about the Gigantes dataset. And I'll also hit on a topic that Miles introduced to you the other day. All right, so just as an intro, really quickly, here's a snapshot from the Illustris simulation. And of course, you can see the galaxies in these bright regions tracing the cosmic web. Now, cosmic voids actually fill these vast underdense regions between the tendrils in the cosmic web. So I'm highlighting a few regions that might be cosmic voids, and you can see they're falling right in those underdense regions. But why even study voids? Well, it turns out voids are very sensitive probes. They're pristine environments since they, by definition, have very little matter in them. They're also a really wonderful complementary probe to both CMB and galaxy cluster measurements. They're excellent for measurements of the growth rate, for example, and they're also really wonderful for physics beyond the standard model. Now, that's because by definition, they don't have much matter in them, so they're more sensitive to diffuse components of the universe. So they're great for studying modified gravity. They're really great for looking at dark energy. And more pertinent to this presentation is they're wonderful for studying neutrinos with. Now, what's interesting is that neutrino free streaming scales are right along the sizes of cosmic voids. Cosmic voids tend to be about 10 to 100 megaparsecs in size. And actually, neutrino free streaming scales fall between 40 and 130 megaparsecs, depending upon the sum of your neutrino masses. So really, cosmic voids are a really interesting tool to study neutrinos with. So let's zoom in a little further into this. Let's build some intuition for the physics and why they're sensitive to neutrinos. So here I'm showing you a snapshot from, well, a halo density field from the Demnuni simulations. And what I'm showing you right here in the still is what it looks like with massless neutrinos. Let's see if this works. Yep, there we go. So now I'm showing you how that density field changes when we increase the sum of neutrino masses. So you'll notice that when we have a higher sum of neutrino masses, we're seeing those dense regions, which are represented by the white and red regions, they become more concentrated. And we're also seeing those tiny little islands that are there, kind of, you see those two in the center, those disappear when we have a larger sum of neutrino masses. Now, in terms of voids, what this ends up doing is that those voids fill the underdense regions. So when we have massless neutrinos, we have a lot of small voids. They're filling those tinier regions between the islands that are in this density field. But when we have massive neutrinos, those small islands between the very dense regions begin to disappear. And so our cosmic voids end up filling a much larger region between those dense areas in this field. And so when we increase the sum of neutrino masses, what we would expect to find is more large voids and fewer small voids. Now, if we look at the void abundance, which is the void size function, and you can think of this as a histogram of void sizes, this is exactly what we see. So in the top is the absolute void size function. In the bottom, I'm showing you the ratio relative to massless neutrinos. And red is the most massive case here, and we'll be comparing it to the black, which is the massless case. And in the bottom panel, you'll see that when we have a large sum of neutrino masses, we see fewer small voids and statistically equivalent to more large voids. Now, the size of voids isn't the only thing that we can look at. We can also look at their distribution in the universe. So now I'm showing you the void autocorrelation function here. And I just want to point out some of the features before we start talking about the neutrino impact. So you'll see this very strong peak in the center of this correlation function. This corresponds to what we call the void exclusion scale. And this is approximately at 2 times the average void radius. Now, we get this peak here because at 2 times the average void radius, voids are clustered like this, their walls are touching. And voids aren't allowed to overlap because if they overlap, then they merge to form a new single void. And so what ends up happening is that we get increased correlation basically at this scale because this is the closest that they can basically cluster to each other. Now, when we add in changing the sum of neutrino masses, what ends up happening is in red, as you'll see in this figure, we actually boost the correlation power at that scale. But let's back up a little bit. How do we even find nothingness? How can I use this in data? So in this simulation, we're going to in this presentation, we're going to focus on simulations, and we build our void catalogs on the Quixote simulations. Quixote is a suite of 44,100 n-body simulations that are really wonderful for understanding the information content and cosmological observables, as well as providing an abundance of statistics to train machine learning algorithms with. And the way we actually find voids is first we look at our galaxy field, and we perform a Voronoi tessellation of that. Then after the tessellation, we perform a watershed transform, which basically merges those small cells, and then we build up our voids from there. And this is nice because this captures a detailed void shape, and this void may sit in the cosmic web like that. And just as another zoom in of the simulation, so here I'm showing you just slicing through a simulation, and you'll see these dark regions. They have very different sizes, very different shapes. These are the cosmic voids. And with the void finding algorithm we use, we're able to actually capture those variations between the voids. And now I'm introducing to you the Gigantes data set that we put a paper out on about a month ago. What's really wonderful is that there's more than 1 billion voids in this catalog suite, representing more than 20 terabytes of data. We have more than 15,000 void catalogs covering a host of different cosmologies, and it's the largest and most realistic set of voids ever released. It's a wonderful, massive data set for machine learning, not only for understanding cosmology, but also for developing interpretable machine learning techniques with, and it's really going to open the field of voids. And here I'm just showing you a table representing the types of void catalogs we have. So you'll see we cover 4 different redshifts, We have Fisher variation, so that's stepping each different parameter, just a single parameter at a time. We have Latin hypercube void catalogs, different resolutions, so really a whole host of different catalogs to use. And here I'm just showing you some quick results from our first analysis of these void catalogs. So these are Fisher forecasts. At the left, I'm showing you forecasts for the sum of neutrino masses and omega matter. Now, in each of these colors are different summary statistics. Purple is the halo mass function, pink is the void size function, teal is the halo correlation function, and green is the void correlation function. And you'll notice that for neutrinos, the void summary statistics are really wonderful, very tight constraints on neutrino mass. And when we combine all of these, we even get tighter constraints, which is really wonderful. Now at the right, I'm showing you a different set of constraints, but really what I want to highlight here is the orientation of these contours. You'll notice that every single one is going in a little bit of a different direction. And this is pointing out that voids not only are great for diffuse components, studying them, but they offer complementary information to galaxies on other cosmological parameters as well. And so as I was mentioning, again, in this figure at right, you see that the combination provides very tight constraints. And voids are very powerful, and what's really interesting for us is that they really haven't been fully explored or fully utilized yet. And so with this simulation suite, it really opens up the study of them, both theoretically and what we can do in terms of constraints on cosmological parameters. Now, just to put some numbers on what these summary statistics are constraining, the void size function puts about 7 times stronger constraints on neutrinos than the halo mass function. And similarly, the halo correlation function puts about 7 times tighter constraints on the halo mass function. Now, the correlation function for voids is 2 times stronger than the correlation function for halos. And when we combine all of them, we get about 18 times tighter constraints on the neutrinos relative to the halo mass function. So adding voids into our analyses really could help us substantially with constraints on these diffuse components. Now, just to kind of drive it home a little bit, here's a comparison of pure halo statistics compared to pure void statistics in red. And you'll notice that, again, you see these contours going in different directions. And while voids are very wonderful at constraining neutrinos, halos are also wonderful at constraining matter, for example. So they do offer complementary information. And then following up on this, as I was mentioning earlier, our void finder is able to preserve the shape in this void catalog. But there are also other techniques to find voids, including a spherical void finder. And what's interesting is that you could actually compare these two different techniques, and potentially they can be complementary, and you could potentially find additional cosmological information in their comparison. And so that would be an interesting study to do. And just to take a look at the differences, you'll notice that in pink, this is the shape-preserving void finder. Orange is using the spherical void finder. These are, again, Fisher constraints for just the void size function. And you'll notice the pink with the shape-preserving finder tend to be tighter overall in the cosmological constraints. So we do believe that shape can add some information there. Finally, just to end with a nice, pretty figure, this is showing you the correlation between summary statistics for both voids and halos. And what you'll notice is that overall, the void summary statistics tend to be uncorrelated with not only themselves, but also the halo summary statistics, which is really great. And this points to the fact that voids do offer complementary information to halos. Now, finally, some applications in terms of machine learning. So here I'm showing you results from a likelihood-free inference. This is interesting because for voids, we really don't have established likelihoods for them. And these plots here are just showing you results from using the void size function. Now, what's great to note is that most of the time we're able to recover the true value within the standard deviation for most cases. So this is pointing out to the fact that, machine learning algorithms with this new data set could provide us a lot of new information. Sorry, the screen just went black up here, so I'm going to look here. Now, finally, I'm going to end with what Miles introduced to you 2 days ago, interpretable pooling operators. Now, at left, I'm showing you again our Fisher constraints on the sum of neutrino masses and omega matter, but this time we're going to focus on omega matter. And I'd like to point out for Fisher, we get about a 22% error on the void size using just the void size function. And with the void correlation function, we get about a 12% error on omega matter. Perfect, thanks. Now, when we use this interpretable pooling operator, the histogram operator that Miles introduced to you the other day, we're actually able to get a fractional error of 13% on omega matter using just the size information of voids. So this is showing you that with sophisticated techniques that we can develop using this new data set, you're able to really pin down cosmological parameters stronger than even our idealized forecasts. So 3 key takeaways from this presentation. Voids can provide competitive constraints on neutrino mass. They have unique information about cosmological parameters relative to halos. And Gigantes provides a massive machine learning data set that can be used not only for the theoretical exploration of cosmic voids, but also to try to develop new interpretable machine learning techniques. Thank you.
Thank you so much, Christina. So are there any questions? Okay, let's go over there. Yes.
Very nice talk. I was curious about how, when you move to real data and you have probably missing data in your galaxy surveys, for example, that could really affect your void functions by like combining or separating voids. I was wondering how you make your technique robust to that. Do you use like an underdensity threshold or something?
Yeah, that's a great question. Let me just pull up a figure as a visualization. So when you apply it to real data, what's really important is your luminosity cut and of course your tracer density. Sorry. There we go. So in particular, something that's going to be sensitive to that is this peak in the correlation function. If you have a different tracer density, a different bias in your halos, this peak is going to shift. And so you do want to understand, you know, what's my fiducial correlation function going to look like given these aspects of the survey that I'm wanting to gain insight from. So that's very important to understand. Now, that being said, because this correlation peak shifts, you know, a fair amount to these different aspects, something that could be interesting to do is to actually use a multi-tracer technique in order to pin down constraints on cosmological parameters more. Because you have such a sharp feature in this summary statistic, I think this would be something interesting to use. And then one follow-up point, so the simulations that we're using here, the tracer density is fairly similar to surveys that will be coming online. And it's actually a little less dense than some future surveys like Euclid, for example. So I think we can expect potentially even better results than what I'm showing here.
Great, thank you.
Can you please elaborate more on how do you recognize the voids using the tessellations?
Yeah, sure. Yeah, I kind of glossed through that really quickly. Let me just pull it up. So we have our galaxy field, and then we do this Voronoi tessellation. And what that means is that any point in space that's nearest to a given galaxy is enclosed in that cell. So we just basically assign all points in space to that cell. Now, the next thing that we do is a watershed transform. And what this means is that we start out with those individual cells from the tessellation, and you can imagine pouring water into those little tiny basins in your field. Now, if you keep pouring water, eventually you're going to, instead of having 2 separate cells, they're going to fill and merge to form a single cell. And so you can keep visually pouring water into these cells until you have a much larger basin. So that's essentially what you're doing with this watershed transform, and that's how we basically merge these tiny little separate cells into what we represent as a larger underdensity between the cosmic web. And that's also why these voids with this void finding algorithm they have different shapes. So they're not necessarily round. They might have like a little strange like curve to them, things like that.
Okay, so on an average, after you determine which of these are like voids, on an average, what's the number of galaxies that lie in a void? Because I can see there are some points, right? And each of them is like a galaxy, right?
Yeah, so it's a good question. It depends on your tracer density of your underlying simulation or data set. So it's more like a tracer density question. I mean, there's not going to be a lot of halos within your void, but there will be some. And they tend to be smaller than what you may find in like an overdense region for halos. But in terms of the number, that's going to be very, simulation and survey specific.
Okay, thank you.
Yep.
Okay, and another short question there. Thanks.
Thanks, Christina. Just one quick question. Is there actually any degeneracy between, for example, this, what would be expected from AGN feedback? Like you're doing n-body simulations here, but if you imagine sort of getting contaminations into the void field from AGN feedback and other feedback processes, do you think that, because that would shrink the voids, do you think that would actually affect sort of like the analysis in terms of?
Yeah, so you're asking basically how the void field would be impacted by AGN feedback?
Yeah, but how, and the constraints on neutrinos.
Oh, yeah. Yeah, so I think it'll impact it a little bit. It's more going to impact, so something I haven't touched upon in this presentation is, and you can kind of see it in this visualization to the right, voids have children. And these are, the basins within them that are small that, we fill up and they merge. So the thing that's going to be more impacted by AGN feedback and things like this, I would say would be the children of voids, because, and also small voids that are in overdense regions, because you're going to have more of this feedback in those areas. And basically, the smaller the void, the more of halos basically can impact. It's just like a proportional impact on the void, I would say. So something that could be interesting to study is, one, how do children of voids respond to feedback? And two, if you just do a cut on your void catalog, only taking the smallest voids, I think that's going to be the more sensitive thing to look at. And that's interesting. We haven't looked at it, but I think it could be interesting to do.
Okay. Well, I think we should move to the next speaker, but we thank Christina again for this nice talk. Oh, for the next talk, we're going to have Ira Wilson, the fault in our spectrum, a no-go on small field models analytics.
Hi, everyone. Thank you. So I work in CISA with Roberto Torota and the Data Science and Cosmology group. And today I want to convince you guys that there's a problem in theoretic cosmology that may topple a 20-year-old tower of cards of sorts. So if you want to take one or two messages from this presentation, is one, the first one is, for the first time in, 20, 30 years, we're giving a rule of thumb of sorts to when it's okay to use your analytical first order perturbations. And then the second thing you want to take is that there's probably no reasonable analytic approximation that predicts the primordial power spectrum with sufficient accuracy given the inflationary potential. So just to give a cartoon of what this process looks like, right? So we basically want to start here, right? Take all the knowledge, all the data that we have here, and glean some insight regarding the high energy regime of inflationary cosmology. That's obviously an inverse problem, which is very hard. So what we do is instead we use the forward problem. However, so just basically we take the inflationary model, we evolve the background geometry, use GR or whatever, particle physics, you get the perturbations, and then you get your primordial power spectrum, you encode it in NS, the spectral index, the running of the spectral index, and so on and so forth. And then you do your favorite MCMC and you get your CMB realization. Great. However, while the MCMC is supposedly a hard problem, that's why you use the forward problem, that box right here is also computationally heavy, because what you have to do is basically solve a bunch of equations, which are time-dependent harmonic oscillators. You stack them up, right, and then you slice them, and then only then you get the primordial power spectrum, which you can essentially put into your MCMC generator. So what smart people have done, namely Stewart in Life, and then Life in Rioto, and then others, they created this bypass, right? They said they showed that the inflationary potential, the shape of the inflationary potential correlates to the shape of the primordial power spectrum. And if you do that, if that correlation is correct, you just stick it up there in your inflationary models, and then you can MC the whole way down, right? So this is the process in a little bit more details. Just to note that the bunch of equations that we solve are time-dependent harmonic oscillators, which do not, as a rule, have any analytical closed solutions, unless you have very specific cases. So this is the first time we actually see the problem with our own eyes, right? So theoretician would have you believe that they can predict the primordial power spectrum if you have your inflationary potentials. That's basically bunk. What I've shown here is that the honest-to-God numerics predict something or calculate something, and the theoretical predictions are about 1% away from that. So just to bring the point home, 1% means you cannot distinguish between NS equals 0.965 or NS equals 0.975, 0.955, right? Both of those ends are actually excluded. So, you know, that's a big deal, especially if we take into account, you know, all of the incredible work that we've seen so far, mainly Chang's talk on Tuesday, for instance, that, you know, we're all condensing our target space all the time, and theoreticians, you know, they have what they have, right? They have only linear perturbation theory, and so they want to try and get to that target area, but that's antiquated. We can't really do that. So just mathematically, what we're doing actually is we're looking at a bunch of Hankel functions, which are the eigenfunctions of the inflationary canonical problem. We know how we start those. Those are just the Bunch-Davis initial conditions, but we don't know how we end those. Especially, there's only, I think, 2 years ago, people have started to look at perturbed Bessel functions in terms of their stability to perturbations. So, okay, fine, we start there, we end there in the explosive limit, no less, which is poorly constrained. For next slide, we're going to use two matrices. So one matrix is the perturbation, the amount of perturbation or the amplitude of perturbation, which is nothing more than your L2 modified norm. So you have your baseline function, and you have your perturb function, right? And you stick it into the L2 norm, and you divide it, you normalize it by the baseline function interval over there. And the asymmetry, which is sometimes we actually take the absolute value of that in order to make it symmetric. But the asymmetry, which is just the distance between two quantities. Okay, so let's talk problems and solutions. So I've already lined those up. So perturbation over Bessel to first order, is that stable or not? Taking the limit at the explosive limit. And you have the so-called bypass relies on this correlation between slow roll parameters at the potential and derivative language and slow roll parameters in the language of the Hubble parameter and its evolution, time evolution. So the first problem was mostly ignored for 30 years or so. But so one notable exception is Wang, Mukhanov, and Steinhardt. Mind you, Mukhanov is kind of the godfather of quantum perturbations. So it's supposedly a big deal, but people basically ignored it anyway. And they said that you shouldn't rely too much on this kind of analysis, that's this kind of first order perturbation, but they didn't supply any limit. And then this, the other problem was addressed by a bunch of people. This is just a list over there, around year 2000, and they tried to develop this correlation to higher orders, right, to make them more correlated or better correlated. However, we've shown in 2018 that this isn't the case, and this is basically useless for small field models. This, I'll gloss over this. You can bring me back to it if you want. So the process of studying, methodically studying this response to perturbation is, okay, so first you take your baseline function. For large field models, you take the closest power law inflation. For small field models, you take the closest monomial model, which is very close to its analytic assessment. And then you use whatever heuristic you want to perturb over these baseline functions. The important stuff is that you have to measure, you have to apply this measure to actually get the amplitude of the perturbation. Then what we do is we simulate a bunch of these models, perturbed models, and we take the results, we bin them in bins of perturbation amplitudes, and in each bin, we take the maximal symmetry. And the reason that we do that is to be able to see if we can trust it or not. Obviously, some potentials will give us okay results, but we want to see if we can trust it or not. So this is for large field models. And you know, the situation is pretty good, I would say. Right? Up until, let's say, 2% or so were golden. Right? We have 0.5% of response where, you know, where we the observables are, you know, you can stomach that deviation. You can even push it all the way to, let's say, 3%. Fine, which is already an improvement on, you know, state of complete ignorance. However, for small field models, the situation is dire indeed. Already at 0.1% perturbations, we have larger than 1% response, which means that probably we can't trust it at all. Even if you believe your linear approximation here, your linear fit, already at 0.5% perturbation in very hot water. And so, fine, the analytic expressions we have so far don't work. Great, let's try and find new ones. So we've simulated about 150,000 models of you know, primordial power spectrum that the models give, right? And we try to fit them using a multinomial function right here. And then after that, we tried the same thing with neural networks. So what we did is we programmed a harness that toggles over many architectures of neural networks, trying to find something that will give us a mean asymmetry of lower than, let's say, 1% or 0.8%. The results of that effort, I won't even show here, I'm too ashamed. But what we did do, though, is we said, okay, fine, so the surface is very irregular. However, maybe we can just zoom in and look at a little piece of heaven right here that is closer to the actual target, the observable target. Fine, that should be better behaved. And indeed, it is better behaved as expected. However, the multinomial approach yields around 1%, slightly lower than 1% for a 7th degree multinomial, which spells around 120 tunable parameters. Okay, fine. How do artificial neural networks do? Well, they do better. However, you know, the first one, the minimal one that yields something of, you know, of actual value is a 10 fully connected hidden layers with 36 nodes in each layer, right? It gives us, you know, great results. Which, you know, the good news is we can now stick it inside an MCMC and find the likelihoods. Great. Bad news, it's fairly model dependent. It requires you to do the, you know, find the 100,000 potentials and filter them out, and then it's very computationally heavy. just to bring the point home, so this Encyclopedia Inflationaris that basically assigns likelihood to each inflationary model is now essentially worthless because it assumes that that correlation holds, but really I've just shown you that it doesn't. So this whole endeavor, which is great, needs to be redone. Not fun. So just to sum up, for large field model, we can have up to 3% perturbation maybe. For small field models, we can not trust analytics beyond 0.1%. And there's no current simple analytical approximation that is feasible. And I suspect, or it's suspected, that none actually exists.
Thank you very much. Are there any questions?
Yeah, nice talk. So maybe I missed the point, but why do you need an analytic expression?
Because the process of turning inflationary potential to the power spectrum that it yields is computationally heavy. So you want to have some analytic correlation between the inflationary potential to get directly to the power spectrum summary, right? The spectral index running, the running of running, and so on and so forth.
But why the neural network is not good?
Why? I don't know. It just doesn't. It just isn't. I mean, seriously.
You mean?
This is a problem. I'm raising a problem that I hope we can address. We as a community can address in the real near future. Because if we can't address it, then that whole Encyclopedia Inflationaris, okay, fine that it's not exact, great. But if we can't address this, we can't even try to make a new one. It's too computationally heavy.
Maybe I didn't understand still, sorry. So you mean that the neural network is not working, or that you don't like it, or?
No, what I mean is that the architectures, all of the architectures that I've studied, right, that are basically simple architectures, fully connected hidden layers with basically your ReLO functions, right? I've toggled over hundreds of them, right? So in layers and in nodes in each layers and so on and so forth in the harness, up to some cockamamie number, crazy number. And so that one, the 10 fully connected layers with 36 nodes in each, was the first one that gave me something of value, right? But already that is highly specialized, because I had to filter out all the results that didn't fit the correct immediate area of the NS that I was going. For the whole let's say, for the whole phase space, let's say, looks like this, highly nonlinear, right? And I would suspect that we would need a huge neural network to actually map potentials to observable. It's not undoable, it's just costly.
Okay, perhaps a short one, because we're a bit behind schedule.
Short question. So what is the dimensionality of this regression? So from the potential to the power spectrum, right? So the power spectrum can be parameterized by 4 or 5 or 10 parameters. What about the potential kind of this dimension?
Right. Okay, so I just did a instance study, right? So what I use to perturb for small field models are a bunch of 6-degree polynomials, right? So it's a perturbation over 1 minus a6 phi to the 6, right? And then I perturbed over it in some way I won't bore you with. Effectively, it maps 3 degrees of freedom to to NS specifically. I didn't show you, but the running of the spectral index and the running of the running is even less constrained. It's totally bunk. So it's 3 to 1. Yep.
Perfect. Thank you so much. We thank Ira for the nice talk. And we now move to Adrian Bayer, the look elsewhere effect.
Thank you. Hi, everyone. I'm Adrian. I'm a grad student at UC Berkeley. And today I'm going to talk to you about some problem in statistics known as the look elsewhere effect, which is coming up a lot in physics nowadays. So just to illustrate the problem with an example, say that there's a medical company that wants to test the efficacy of a drug for treating a particular disease. And so it tests this drug against 100 different symptoms that this disease has. So it tests it against headaches, it tests it against nausea, tested against muscle pain and breathlessness, and it finds that out of these 100 symptoms, only one of them is cured by the drug. And so muscle pain is reduced in 99% of participants, but there's no significant change in any of the other symptoms. And so the medical company wants to know, does the drug actually cure symptoms of muscle pain? And the answer is most probably not. And the reason for that is by testing 100 different symptoms, it's very likely that one of these symptoms will result in a positive result just due to some statistical fluctuation. And so when you assign the statistical significance of this kind of hypothesis test, you have to take into account the number of trials that you're performing. And so this is really very relevant in physics nowadays because physicists are looking for signals in very large continuous data sets, often using machine learning. And one classic example is exoplanets. So you have some telescope, for example, looking out into space for maybe 1 month long, getting lots of data. And that will return some time series with many, many peaks. And you look at each peak and you ask, is this peak an exoplanet? Is this peak an exoplanet? And many of these peaks will just be noise. And so by checking all these different peaks and massive data space for a signal of an exoplanet, you're performing multiple trials just like the medical company was. And you need to take into account this effect when you assign the significance of detecting an exoplanet. And the same thing is true with detecting gravitational waves. And also in high energy physics, when you're looking for new particles like the Higgs boson, you're scanning a wide range of masses to look for some particle resonance. And so just to illustrate this with an example from cosmology, say you have some model of inflation, which has the standard lambda CDM power spectrum, which is your null model, and it's perturbed by some oscillatory feature, which is an amplitude A, frequency omega, and some phase phi. And so what you do is you get some data from Planck, for example, and fit your model to the data, and then plot the projection of the likelihood as a function of the frequency omega, which is what is shown on the bottom left. And what you see is there are many, many peaks throughout omega space. And naively, what you might do is take the maximum likelihood, which is around 3,600, and see that the 2 delta log likelihood at that peak is around 16. And so naively, you might just take the square root of that and say that that's a 4 sigma detection. And wow, you know, you've discovered inflation. But really, that's the incorrect conclusion, because by scanning such a wide range of omega, you've tested many, many different hypotheses. And so you have to correct for this when you assign the significance of this signal. And so how do you do this? So frequentists typically would use the p-value of the likelihood ratio. And this is the probability that the likelihood that you observe is above some particular threshold. So in the previous example, that would be, what is the probability that I find a peak which is at 16 or higher? And so you need to somehow compute this value in order to assign the significance of a detection. But the problem with this is that the likelihood only considers the height of that local peak, and it doesn't take into account the entire parameter space or all the other peaks in your distribution. And so just to illustrate this problem, if you just look at the omega values between 0 and 1,000 in the top left, you see that the highest peak is around 15 and 2 delta log likelihood. But then if you carry on looking to omega equals 2,000, then you find a peak just under 20. And if you carry on looking all the way to 4,000, you find that there's now a peak above 20. And so essentially by looking elsewhere in the parameter space and scanning a very large parameter space to look for a signal, you're increasing the probability that you're going to find a high peak. And so this shifts the p-value relation as a function of the maximum likelihood. And you need to be able to model this effect in order to correctly assign the significance when you want to claim that you've detected something. And so how does one compute the p-value given this look elsewhere effect? And so there's 2 typical routes that people take. One route is numerically. So for example, if you want to know what a 5 sigma detection is, that corresponds to a p-value of 10 to the minus 7. And so what you do is you'd simulate make a simulation of your data without a signal 10 to the 7 times or more than 10 to the 7 times, which is 10 million simulations. And then you'd see how many times do you get a peak of a particular height or above. But that's extremely expensive, especially when your model is complicated or maybe it relies on some machine learning techniques, and it's kind of unfeasible. And there are some faster methods to do this, for example, developed by Gross and Wittels in 2010. But this also requires a few thousand simulations typically. And another option is to compute the p-value analytically, but this is kind of unfeasible for complicated models. And so in our work, we seek a faster method that can be applied generally. And to do that, we take inspiration from Bayes factor. So Bayes factor is equal to the ratio of the Bayesian evidence between the hypothesis that there is a signal in your data and the hypothesis that there's no signal in your data. So it's the likelihood ratio, but integrated over the parameter space. And so if you take the Laplace approximation at a single peak, you find that Bayes factor is essentially just looking at the likelihood ratio multiplied by this extra term, which is equal to the width of your peak, the width of the posterior peak, divided by the width or the volume of the prior. And so this is essentially like the number of trials, or 1 over the number of trials, and takes into account the look-elsewhere effect for free, basically. And so just to illustrate this, what you have your peak, which is the black line, and the likelihood ratio essentially gives you the height of the peak. And that's what we were looking at earlier. But by looking at Bayes factor, you also take into account the width of the peak and the width of the entire parameter space. And so this green to blue ratio is essentially telling you the number of trials that you've performed in order to find this peak. And it essentially corrects the likelihood ratio for the look-elsewhere effect. And so in our paper from 2020, we find that you can define this new statistic, QS, based on some combination of the Bayes factor and the likelihood ratio, such that the p-value is just a function of this new statistic. So the look-elsewhere effect is essentially being cancelled out by adding the Bayes factor and the likelihood ratio in this way. And so by using this, you don't need to perform any simulations. You just compute Bayes factor, you compute the likelihood, and find the p-value from that. And to show our results, so each color here on the left-hand plot corresponds to a different prior volume. So the purple line is showing when your prior volume is 10, and the blue line when your prior volume is 100, and the red line when your prior volume is 1,000. And so you see that from the dotted line, which considers the likelihood only, as you increase the prior volume, your p-value relation as a function of the statistic is changing, and that's the look-elsewhere effect. However, when you look at the dashed lines, which corresponds to the QS statistic, which is based on Bayes factor, all the lines agree very well with each other, and also are very close to the black line, which is the theoretical equation from the previous slide. So essentially, by using QS, you know the p-value generally, regardless of what prior volume you're scanning and what width of signal you're looking for as well. And so revisiting the model of inflation from before, the naive 4 sigma detection is only a 1 sigma detection after correcting for the look-elsewhere effect. So it's nothing to be excited about. And then, so one question you might ask is, well, Bayes factor can also be quite complicated to compute. So what if you don't want to compute Bayes factor? So one thing we're looking at is that previously we were always looking at the maximum peak. So what is the height of the maximum peak and what is the width of the maximum peak? But what if you also look at the information from all the other peaks in your distribution? So for example, over here on the top plot, you have the difference in height between the highest peak and the second highest peak, and then the difference in height between the highest peak and the 10th highest peak. And so by using information from the difference in heights of the peaks throughout your distribution, you can also essentially calibrate the p-value to a pretty good accuracy without computing Bayes factor. And this is extremely cheap because you just need your data with some peaks and compute the difference in peak height. And from that, you can get the p-value, which we show on the bottom right for some Kepler exoplanet example for different kinds of stellar noise. And it shows pretty good agreement with the black line, which is the theoretical line that we have. And so to conclude, the summary is that volume is important when you're trying to do a hypothesis test, and that allows you to develop a fast method to account for the look-elsewhere effect. And there's many potential applications for this throughout physics, for example, exoplanets, gravitational waves, energy physics, and also potentially in machine learning, for example, for generalization. And since I have time, I guess I can show you an extra slide. So neural network generalization, it's a well-known effect that in order to find a machine, to fit a model which generalizes well, you want to find a dip in your loss function which has a large volume. So on this right-hand plot on the left-hand side, you see that the loss function has quite a wide volume, and the decision boundary on the top is very smooth and looks well behaved. However, if you have a very narrow loss function, then the decision boundary is typically very rugged, and a slight perturbation to your parameters is going to screw everything up and mess up your decision boundary. So the concept of having a large volume when you're picking your model is important when it comes to machine learning and having generalizable models. And so it's possible we could use apply this technique to find the model the best model, so to speak, in terms of the volume of the loss function and not just the height. And in addition to that, we're also actively working on more efficient ways to compute base factor. For example, using normalizing flows, which is some of the stuff B-Way was speaking to you about yesterday, using the same technique. And yeah, that's all I really have to say. Thank you.
Thank you very much. Any questions?
Yeah, thanks. This is great stuff. I had one question about the second to last slide before the conclusions. How important is it in this technique that you're finding the sort of rank ordered list of the peaks? Is it a problem in I mean, sometimes we use these methods in super high dimensional parameter spaces where it's very hard to find even the single highest peak. What about, could you find first, second, third, fourth, fifth?
Definitely, this technique definitely would break down more than in high dimensions. The rank order isn't extremely important. Like the dependence of if you miss a couple of peaks along the way or you get the order slightly wrong isn't a big deal, because I didn't write down the equations, but it's a logarithmic dependence, so it's kind of small. It's not important if you miss some. But yeah, I expect if you go to very, very high dimensions, then this particular technique with peak heights might not work so well. But we haven't tested it, and this example here is 4-dimensional, for example. But yeah, it would definitely be interesting to test in high dimensions.
Great, thanks.
I have a question regarding the calibration that you propose here, which is the difference between the maximum and the minimum peak. Like one of, I guess, the earlier motivation plots where you were showing for the cosmology problem, right? Like where you had like all the omegas listed. I'm thinking that, but if by chance, like you can have like a high peak, like due to statistical noise, like by chance you could also have like the lowest peak being unusually low by chance as well, right? So wouldn't a calibration with sort of the median height of peaks versus the tallest peak make more sense, so that like you're not kind of like amplifying
Are you saying that use the highest peak?
As opposed to like doing the difference between maximum and the lowest peak, like doing between like the maximum and the maybe like the median height of the peaks, or the median peak, something of that sort. Yeah.
I mean, I guess the way we derived it is that for basically, if you take the maximum peak and any peak below, you can write some equation in terms of what ranks that peak is and what the p-value is. So taking the median maybe is something one could do, but I would need to go through the math and figure out how to translate that. But yeah, definitely taking maybe some sort of average over maybe the second peak, the 10th peak, the 20th peak. And yeah, we discussed this in the paper as well, like which peak. But yeah, median is a good idea.
Okay, thank you.
Yes, very interesting. I have a quick question on your number of trials, which is obtained from the width of the peak divided by the length of the line. It was just not exactly clear to me why that's justified, and why not just use simply the number of bins? Because in discrete data, there will be a discrete number of points in this periodogram.
This is for continuous data, essentially.
In reality, it's always discrete. Well, in practice, the data will be...
In practice, the data will be discrete, yes. But when you plot the peaks, like it's not going to be discrete at like each peak height. You're kind of going to fit and find some continuous distribution eventually. And so I guess why not the number of peaks? I guess I don't know, the easiest explanation is just this Bayesian influence, which motivated us to consider the peak volume, and it works very well. I guess maybe the problem with using just the number of peaks is how do you define what a peak is? Some of the peaks can be conjoined, and sometimes also when you extend actually beyond. So far what I've been speaking about is like working under the plus approximation, where you have lots of nice peaks in your distribution. But as you go to more complicated distributions, you get like complicated peaks, and the Laplace approximation isn't so good. And in that case, you actually have to integrate the whole Bayes factor to compute the p-value correctly. And so what this plot is showing, some preliminary work, is that really the true thing to do is not just to take this approximation of prior volume over posterior volume, but actually to integrate the entire of Bayes factor, like do the full integral rather than just the Laplace approximation. And in this plot, we show that doing the full integral agrees very, very well with the theoretical line. So it seems like it's something deeper than just looking at peaks and the width of peaks. Really, it's Bayes factor, which is telling us what the p-value is. Does that answer your question? I know. Okay, maybe we can speak more about it. Yeah.
Perhaps one, if there is a very short one.
Mm-hmm.
Could you please use your seat mic?
The selective inference setting is something where, for example, you've got 100,000 genes and you wanted to see whether there's like some sort of significant gene among the 100,000 ones, and you first threshold them, and then you get like 100 of them, and then you say, oh look, among those 100, I've got a lot of effect, but it's because you thresholded them. So I'm just wondering, because I was completely unfamiliar with that framework, whether you know of this body of literature and whether there are links to what you're presenting, because it seems kind of adjacent.
I do know that in like genetics, there are people doing similar things. I think the key difference there is that often the data is discrete, because comparing one gene to one phenotype, where say we're looking at continuous parameter space. But there could be some analogies to explore. And yeah, maybe it'd be worth discussing that offline. But yeah, off the top of my head, I don't know the exact relation between what we're doing and what they're doing.
All right, cool.
Thank you.
So we move on to the next speaker, Max Lee, and we thank Adrian again. So Max Lee is going to talk about gradient-based inference in cosmology using MADLens.
Thank you very much. How does this work?
Yeah.
Awesome. Cool. My name is Max. I recently finished my undergrad at UC Berkeley, where I was working with Vanessa Bohm on the creation of a weak gravitational lensing simulation called MADLens. And since graduating, I've been working on now applying this weak gravitational lensing simulation to perform a cosmological parameter inference. And yeah, I wanted to talk a little bit about both of these projects. So just briefly to start with some general weak lensing, we start with background galaxies, scale structure of the universe, and some telescope or observation. These background galaxies have some intrinsic ellipticity and magnitude, and as light travels through the large-scale structure of the universe, their shapes are perturbed, and the weak lensing field that we get measures the coherent distortion between these background galaxies, and is a tracer of the projected matter density along a line of sight. So weak lensing of galaxies is sensitive to the total matter parameter, the amplitude of matter fluctuations, sum of neutrino masses, time varying dark energy. But what we're mostly interested in our work is looking at the total matter parameter and the amplitude of matter fluctuations, sigma 8. And the reason we're really interested in this is because I'm sure we're all aware of the tensions in the standard cosmological model right now. And so here I have the DES year 1 results, where it shows that depending on the tracer you're using to measure cosmological parameter values, you tend to find that you get different constraints. And so this can be indicative of either possibly new physics that exists, or maybe the data that we have isn't enough, or maybe it's just that we're not performing optimal analysis on the data in general. But right now is a really exciting time to be in weak gravitational lensing because of the future data prospects that we have. So for example, the Vera Rubin Observatory will be pulling in 20 terabytes of data a day, which is really exciting. And this means that we have the opportunity to possibly answer the question of where this tension is coming from. But in order to do that, we also need to re-examine the ways that we're performing our analysis on weak lensing data. And yeah, so for weak lensing analysis to continue, we really do need to improve. If for it to improve, we would like to utilize and extract the full information content from these upcoming surveys. And this was the impetus behind MADLens, which is a weak gravitational lensing simulation that was built with the idea of performing field-based inference in mind. So how does MADLens work? Well, we start off with some random initial fluctuations in a cosmology. So we can think of this as some delta and some omega and sigma. We perform structure formation. So we generate this through or progress it through an M-body simulation. We use FastPM. And then we project this in through a lensing kernel to get a convergence map, which we can think of as just some mapping between our initial conditions and our initial field and some function f of those conditions. So what makes MADLens really cool is not only can we go forward, but we can also go backwards. And by this, what I mean is we can take the derivative of the entire convergence map with respect to the initial conditions and with respect to the cosmological parameters. So that's going to be important for inference. But beyond that, MADLens is more accurate than conventional light cone codes. So here I've plotted the theoretical correlation function in Fourier space from HaloFit, along with a MADLens weak lensing simulation. And we see that they match really well up to a really large L, compared with what we would consider, I guess, a conventional light cone code, which fails much sooner than MADLens to match theory. And one of the reasons that we perform so well is because we use baryonic corrections to our simulations. We use a method called particle gradient descent, which was created by Biwei Dai. And so this essentially learns baryonic parameters from hydrodynamic simulations and allows us to improve or adjust the positions of our dark matter particles based off of what the baryons are telling us. And this gives us an enhancement in the accuracy of our simulations. Beyond that, MADLens is really fast. So this bottom plot just shows a couple of different redshifts. And we see that depending on the number of ranks we're using, we have different timescales. But this was a pretty large box of, I believe it was 256 cubed. And regardless, we're able to get pretty fast simulations with a pretty low computational requirement. So what does this all mean for cosmological inference and using MADLens? Well, the way that I think of it is it kind of turns it from an inference problem into an optimization problem where we're just using gradient descent to find the minima of some log posterior. So this opens up the possibility to use quasi-Newton methods with inference, and we don't have to make any simplifying assumptions from the field that we have. We can just go from the full field of our simulations and from the data. So, for example, initial mode reconstruction could look like this. We get some data from a telescope, and from that data, we then guess a cosmology and we guess some random initial field. We simulate weak lensing using MADLens. We compute the loss function between the data and model, and then we backpropagate through the entire process using the derivatives with respect to the initial conditions to get to eventually to update our initial random field and eventually converge on the true initial conditions. So this is a plot from one of our preliminary reconstructions. We have 5 different redshifts going from 0.5 to 2.5. We're using, oh, wow, I realize my mask is still on. That's awkward, sorry. We go from 0.5 to 2.5, and yeah, so we used LSST-like systematics and noise that we put on top of the data. So this was simulated true data. And the bottom shows the final field reconstruction. So after going through the process of performing LBFGS optimization, just as I showed in the last slide, and doing this backpropagation, we were able to get results that match really well to the initial data. But ultimately, this isn't what we're after. What we want is cosmological parameter constraints, right? So the question then becomes, how do we go from initial mode reconstructions to a cosmological parameter constraint? And the way we do that is borrowing from methods that were created by Uroš Seljak and Chirag using the method of maximum posterior mass. And what this means is that we start with an initial mode reconstruction, and then we marginalize over the latent space of those initial modes to obtain just a space that has our cosmological parameters in it. We then take a derivative with respect to cosmological parameters in that gradient space. So it's just one gradient descent step, allowing us to update our cosmology and then perform this process again. So we repeat this until we converge: initial condition reconstruction, marginalization, gradient descent step, and updating cosmology. So to date, we've been able to do this entire cycle just one time. So the next plot that I show is what we hope to achieve. The first 2 points we have achieved. The other points I filled in because it's what we want and what we hope to see. So I'm going to quickly put arrows so that you know what's real and what's not. So in this plot, we started with a fiducial cosmology that was 20% above the actual or the Planck values of omega m and sigma 8. We performed initial condition reconstruction. We were able to do our Laplace approximation to integrate over the latent variable and get into our cosmological parameter space. And this was the first point, is the update step that we got. So before we continue taking more steps, we're now pausing to look at why we didn't step farther in the omega m and sigma 8 space, and why it took so many function evaluations. So this is something that we've just recently started looking into, so stay tuned, but I think this is promising that we will eventually move forward in the right direction. So yeah, one of the challenges, I guess, that we are facing is the large computational requirement and number of simulations that we need to converge on this. With that being said, there's other methods such as Hamiltonian Monte Carlo or sampling that are currently being used, and we do think that we're going to be able to do parameter constraints with less iterations or samples than what they've been using. But that being said, we'd still like to do it in a computational tractable way. Some of the advantages, again, from this are that we're using the full field for our parameters constraints. We're not making any simplifying assumptions. That MADLENS is fast and it's accurate to the point where we can actually simulate these stage 4 surveys, which is exciting. Also, MADLENS can be extended to other cosmological parameters. So we can easily integrate taking the derivative with respect to neutrino mass or time varying dark energy if we wanted to. And it allows for easy implementation of systematics and putting in possible masks or noise that might be on future surveys as well. So just to sum everything up, we've written this really cool weak gravitational lensing simulation that's fully differentiable, it's accurate, and it's fast, and we're using it to perform full field cosmological parameter inference. And while we've developed this analysis pipeline, we now want to optimize it to get better results. And we look forward to presenting these results in the near future. I'm happy to take questions.
Thank you very much. Questions? Sure.
MADLENS, like there is a plot where you show like halo fit and then like the actual data, and somehow MADLENS was following the halo fit really well, but not the actual data. Do you think that difference in the small scales might be affecting? Actually, I don't know if you can find the plot, but did you really want to go? It's going to take a while.
No, go back. So you said that there's, oh, actually, I think it's right here. Okay.
Yeah, right here. So are you trying to get MADLENS to fit halo fit or the conventional Lycon?
So we want it to fit halo fit. If we hit halo fit, it means that we are more accurately reproducing smaller scale effects from MADLENS. compared to what we would think of as the conventional light code. So one of the really cool things about this plot actually is MADLENS is a 256 cubed box in this case, and we're more accurate than what we would call this conventional light code, which is 1024 cubed box.
That's right.
So this is more of a I guess a selling point to the baryonic corrections that we're using from the particle gradient descent in MADLENS.
So the related question just to the plot where you do initial conditions reconstructions. Yeah, I know, but it seems like you're missing all the small scale features in the initial condition reconstruction at a lower redshift. And I'm curious if you think there's some improvement that you can imagine going that direction.
That's really interesting and a good question. I haven't fully thought through how the small scales would impact that. I do know one of the reasons that the reconstructions look like they've almost been smoothed out a little bit is that we've applied a filter during the backpropagation process. So what we noticed was that when we perform the reconstructions, we get these really weird small scale effects that look almost like blots of power in our reconstruction that we couldn't really explain. But what we found was that when we put a filter on, specifically on pixels that were close in the light cone, it was able to tamper it down. And so we think that it had to do with these pixels close in the light cone creating weird effects that larger out or farther out. That filter has definitely caused some smoothing.
Max, may I comment on this as well?
Yeah, sure.
Once you're done.
Sorry?
Yeah, I was just going to say, I mean, part of this is just the fact that we assume realistic noise here, right? So it's kind of like, think of a Wiener filter. So you have a signal over noise kind of filtering here, depending on, so on the small scales, we have high noise to signal. So that's where the reconstruction will suppress power. So I think this is completely expected. And we also did a comparison to a Wiener filter, right?
Yeah, we've compared to Wiener filter estimates as well.
Yes, and we saw that it matches, yeah, so I think we're good.
Okay, perhaps only one there, if it's short, we're a bit late.
Well, I have two, but I think if you are short of time, I would like to know what are you showing there in the orange curve? So what do you mean as conventional light cone?
Sure.
Because, I mean, I think there's lots of papers that use similar approaches with that kind of box size and stuff. They reproduce the power spectrum much better. So I just wanted to know what you mean with conventional light cone.
Sure. So in this case, the conventional light code is MADLENS. So it's the same thing as the green curve, but without PGD or our particle gradient descent, which accounts for baryonic correction. So that's turned off. And we also have a method of interpolation, which also boosts the accuracy of the positions in the M-body simulation. So they're essentially the same without baryonic corrections. And we can see that with the baryonic corrections, we're able to go up to much smaller scales and reproduce the correlation function better.
Okay, I'm still confused because all of it then doesn't have any baryonic effect.
Sorry, say again?
All of it doesn't have any baryonic effect then as far as I know.
I haven't thought about that. Sorry.
Okay, let's chat on offline. It's
okay, perhaps we should move to the last talk of the section, but we thank Max again.
Thank you very much.
Okay. Oh, this one, right? Okay. Hi, I'm Alina. I'm a second-year grad student at Columbia, and today I'm telling you about weak lensing peaks. So this is based on the project we just did with my advisor, Zoltan Hyman, and also together with Brian Liu, who presented yesterday, and with Jose Manuel Zoria Mattia. Did I point this? Oh, okay. So as we know, weak gravitational lensing has shown to be a very powerful cosmological probe because it traces all the matter in the universe, both known and unknown, as well as its expansion history. But now, as these surveys are becoming larger and more precise, we are now looking deeper on small scales where the mass fluctuations are not linear due to gravitational collapse. So in order to take a full advantage of the small scale information, one of the possible things we can do is to use higher order statistics to capture that information. And one of those non-Gaussian statistics that we can use are the weak lensing peaks, which are defined as the local maxima in the weak lensing maps. So in the weak lensing convergence maps, they would trace the overdensities in the large scale structure. Now, before I go on to the rest of this talk, why should we specifically focus on the peaks? Because there are many other non-Gaussian statistics that have been proposed. Well, first of all, weak lensing peaks have shown to give us comparable constraints to the more traditional statistics, such as the power spectrum. So this was shown both using simulations by Kradiceville 2010 and also using the Canada-France survey Stripe 82 data and also the KITS 450 data. But more importantly, weak lensing peaks serve as a very useful complementary probe. So it was shown once again using simulations that it improves the figure of merit by about 40% when used in combination with the 2-point correlation function. And also using data, the CFHT lens data, it was shown that the constraints are improved by a factor of 2 compared to using the power spectrum alone. And also more recently, a precision of 3% was reached on the sigma 8 parameter using the peaks together with the 2-point correlation function on the DES year 1 data. Okay, so now that I've hopefully shown some ways in which peaks can be a very useful statistics to use, we would like to understand the physical origin of peaks better. So unlike the power spectrum, for which we have an analytical prediction and the behavior of which we seem to understand well, we actually can't analytically predict peaks, and we don't yet fully understand them. What has been shown so far, however, is that the low significant peaks are associated with groups of halos along the line of sight, whereas the high significant peaks with single massive halos along the line of sight. So once again, this was shown using both simulations and observational data. Now, this halo-peak connection inspired now analytical models for predicting peak counts because we would like to avoid the computational costs of the n-body simulations for the larger surveys. And one of the models that I would like to highlight here is this publicly available code called Camelus, which is a halo-based stochastic model for predicting peak counts, which draws halos from a mass function, assigns them an NFW profile with a concentration parameter based on its mass, and then places them randomly in a simulation box. So Camelus works generally well, so the peak differences are within 20%, but Mattia 2016 has shown that still the n-body simulations have larger, more tilted contours, and that Camelus doesn't work as well for precision cosmology. So the question that we wanted to answer in this work is whether halo models in general, such as Camelus, if you take into account realistic profiles and clustering, can explain all the weak lensing peaks. So to do this, we use our suite of Gadget 2 n-body simulations, and we use a halo finder called Rockstar to identify all the halos in our simulations. And then we create new simulation snapshots based on the material from halos alone. And we ray trace our weak lensing maps using a lens tools package for weak lensing analysis. So here you can see an example single realization weak lensing maps from our full n-body simulations on the left, and then the halo only and non-halo material. So you can see nicely this decomposition of the large scale structure into the two different components. Oh, and these are the convergence maps, which are related to the projected matter density. So we apply this to our suite of 97 n-body simulations, as shown here, spanning the omega matter in sigma 8 grid. And here's just an example peak histogram for our fiducial cosmology. So the top pair of panels correspond to the smooth maps, whereas the bottom panels are smooth maps with galaxy-shaped noise. As you can see, even from visually looking at these histograms, the differences in peak counts across all bins exceed a % level in most cases. So the median difference for our smooth, noisy maps is about 10%, while the maximum difference can reach up to 100%. So what we see here is that halos don't explain all the peaks. And in particular, if you look at the upper plot, in particular, the negative peaks. Now, in order to see how these differences are seen in the cosmological constraints, we now use an 8-bin peak count histogram as our observable. We assign our fiducial cosmology from the full n-body simulations as our data vector, and assuming a Gaussian likelihood and a constant covariance from our fiducial cosmology, we use a standard Bayesian approach to now build the credible intervals. So on the left, we have our original size maps. As you can see, the contours are very similar, but they already differ slightly in their areas and their tilts. But now we'd like to extrapolate this to larger surveys. So we scale our likelihoods for surveys that are 10 times and 100 times larger. And what we see is that the credible contours cease to overlap for surveys that are around 100 degrees or greater. So we expect that for current and future surveys, using halo models for predicting peak counts would result in biased cosmological constraints. So just as a reference, both current and future surveys are expected to be much larger than 100 degrees. Now, something that we wanted to check after seeing how much the contours differ, even at just 100 degrees, is whether the material that's immediately surrounding the halo, so on the peripheries of halos, can explain the remaining differences in the peak counts. So for that, we now create new snapshots in which we include all halo particles, along with the particles that are within a certain number of virial radii to their closest host halo. And what we find is that you need to go out at least 15 virial radii to be within 2% residuals for our 8-bin histogram for the noisy maps. Now, because at higher redshift, the halos are more diffuse and they're spread out, we're actually including much less material at higher redshift. And so in order to see whether that can make any difference in our peak histograms, we also repeat this process, but we now include a fixed number of particles at each of our redshifts. And what we find is that you need to include at least 80% of all particles to be within 2% residuals. So the main takeaway, I guess, from this is that the material that's very far from halos is important for predicting peak counts. So using halos alone or the material just outside halos is not enough for precision cosmology with peak counts. So just to summarize, we have shown that the halos don't account for all weak lensing peaks at the % level. So even though models like CAMLAs do pretty well, even if you include all the realistic clustering and density profiles based on the n-body simulations, you still don't get a % level accuracy. Now, I didn't show this plot here, but we also looked at which of the components of our halo models has the biggest effect on predicting the peak counts. And we saw that halo clustering actually has the biggest effect. So if models such as CAMLAs were to incorporate at least halo clustering, they would do a much greater job at predicting peak counts. And once again, we showed that you get biased results for surveys that are as small as 100 degrees squared. And some of the possible ways that we suggest that the halo models could be improved is to incorporate other elements of the cosmic web. In particular, voids could be very useful for the models for predicting peak counts because those are expected to reside farther away from halos and also represent the underdense regions where we expect to see the negative peaks that we didn't account for. And also filaments, which are prominent features of the cosmic web as well. Now, there are some limitations to this work. In particular, we didn't account for any baryonic effects, which have shown to have some effect on the peak counts. But even without that, our result is the main takeaway of this is that we need the material that is outside halos for predicting peak counts, and that still remains a valid conclusion, I guess. yeah, and that's all. If anyone has any questions, let me know. Thank you.
Thank you, Alina. So any questions? Yes.
Yeah, thanks, Alina. Very nice. I just have one question. What was the noise level of the maps that you used to conclude that there was a bias for the surveys greater than 100 square degrees? Or did you look at this as a function of the noise level, like the shape noise level or the source number density?
So wait, what do you mean by the noise level of the?
Well, just your weak lensing maps will have some level of noise that's proportional to the number of source galaxies per square arc minute.
It's like 25 galaxies. Yeah.
Okay. Okay.
So like HSD, I guess. HSC.
Yeah, HSC. Like. Okay. Thanks.
Any other question? Okay. Let me check online. If not, we thank all the speakers for the very nice talks today, and we can close the question.